Hey guys, welcome to Module 13. This week we're going to talk about machine learning and some of its applications towards web security. Last semester at the end, I got a lot of feedbacks and people looking for a couple new topics, and machine learning seemed to be the number one new method that people were interested in learning about. So Ross and I went ahead and devised an entire module devoted to machine learning. This is the last module that actually has course content in it. Module 14, we're going to have the final exam. So a couple questions from this module will be on the exam. There's a quiz this week as well, and a discussion also, but other than that, there is no assignment. So I'd say pay attention closely, but you can only expect maybe a handful of questions from this module to appear on the final. We're going to talk about some of the introductory methods in machine learning and sort of what the goals of machine learning are and the different types of machine learning. We're going to look at linear regression, and then in the end, we're going to look at a neural network and how a neural network makes decisions using something called a perceptron. So we hope you find this lecture very interesting, so let's get started. You may hear a number of different definitions for what machine learning is, but there is a formal definition that exists, and it's stated right here as follows. A computer program is said to learn from experience E with respect to some task T and some performance measure P if its performance on T as measured by P improves with experience E. Probably a little bit better to use an example here to make the definition fit a little bit better. So let's think of it this way. Let's say the task T is to, let's say, automate traffic. Okay, so we're trying to come up with an intelligent traffic light that is able to pass the most traffic during rush hour. So let's say from 5 to 6 p.m. So our task T is to get as many cars through an intersection as possible. Okay, that's our task, is to pass the traffic. The experience E, of course, as each day goes on, we learn a little bit more how well our algorithm did on day one. We run it again on day two with perhaps some minor modifications, and we get another performance measure there. And same thing with day three and so on. Okay, and then we also measure the performance P. So given that our task T is to route traffic efficiently through an intersection, the performance measure P might be the number of cars that we're able to pass during rush hour. Okay, so in this case, T, the task, is passing cars through a traffic light. The experience E is the results that we get from each day. And the performance measure P is specifically the number of cars that we're able to get through an intersection in an hour. Okay, so it's much easier, I think, to understand this informally. So we deal with a model in machine learning. So your model is basically your algorithm. So it could be linear regression, it could be a neural network, it could be a random forest. There's a number of different models or algorithms available to use in machine learning. And usually we train them on some data. So we give them a bunch of data sets which would correspond to E and P above. And we train that model and say, hey, here's how the data was on day one. Here's how it changed to day two. And over time, we can begin to make more accurate predictions about future occurrences of whatever it is that we're modeling. Okay, so the model is revised iteratively. We look each day and we see how that performance measure P changes. If the performance measure gets worse, we're going to make changes until our performance measure improves. Okay, and we're going to keep doing it so long as it improves until the return is negative, until we stop getting improvement. Okay, so we're going to talk a little bit more formally and also informally on the next few slides what this actually means. Within machine learning, there's two main types of problems that we're interested in solving. One is called a classification problem, and the other one's called a regression problem. We're going to talk about both of those right here. The first, you see a classification problem. You can see that the inputs to the trained model are then mapped to a category label. So what that means is, based on whatever the input is, in our case we have an application or an email as a potential input, we're looking to try to map that outcome to one of a number of, let's say, bins or categories. So in the first example here, I'm asking you to give me an application. So let's say you give me an APK file, an Android package file like the one we learned about from the section on mobile computing a few weeks ago. So you hand me an APK and you ask me to make a prediction as to whether or not this application is vulnerable or not vulnerable, because there's only one of two possible outcomes here. And the same thing with the email problem here. If you hand me an email and I have a trained model, let's say I train my model on millions and millions of pieces of spam and millions of pieces of legitimate email, and then you hand me an email and you ask me to tell you just very simply, does this fall into category A of being spam or category B of being not spam? So the number of labels or the number of categories or the number of bins, whatever you want to call them, is not really bounded too tightly. You can have 2 bins, you could have 3 outcomes. Let's say if you were playing cards and you wanted to know, okay, I have this hand, is it likely to be a win, a draw, or a loss? Okay, so that's an example with 3 categorical labels. Okay, so you can have multiple and various amounts of categories, but the classification problem basically tries to take an input and it maps it to a very discrete category. Okay, so when you think classification, think the outputs are discrete values. The regression is a little bit different, however. As you can see here, the regression takes an input, but then it maps it to some real valued output on a continuous interval. So rather than trying to say, is this application vulnerable or not, or is this email spam or not, the question that regression is asking is, give me the percentage likelihood that this email that I'm handing you is spam. So as you know, that the percentage, our response, the percentage of likelihood that that email is spam could be anywhere from 0% all the way up to 100%. So notice that interval from 0 to 100% is a continuous real valued range. They're all real numbers on that range. Okay, and the range is continuous as opposed to just saying, is it vulnerable or is it not? Regression basically asks you for a number. Okay, and that number could be from anywhere on a wide range. So one good example of this is to predict what your house is likely to sell for based on square footage. So you could go on to Zillow and let's say you have a home that's 1,500 square feet. And you go on Zillow and you look at the other prices that were also 1,500 square feet, right? And then you look to see the prices that those homes sold for that were of similar size to your home. So we could plot them on a graph, and we could use an algorithm which we'll see coming up here shortly called linear regression. We could draw a best fit line through the data, and then we can basically take the home prices that had similar square footage and use that to predict what your home is likely to sell for. Now notice we're not asking, is my home likely to sell or not? That would be a classification problem. Will it sell yes or will it sell no? In this case, I'm asking, hey, give me your square footage of your house and I'm going to predict the price that it's likely to sell for. Okay, so obviously that's a value on a continuous interval. And the same thing with predicting the likelihood of an exploit given the number of lines of code that are contained in an application, let's say. So if I write a script, and let's say my script has 100 lines of code, it might have a certain likelihood of some exploit existing in it, because that's a pretty small amount of code compared to something like Windows, the Windows kernel, right? The Windows operating system is about, I think last I heard, 3 or 4 million lines of code long. So if I were to ask you, hey, how likely is it, what percentage of likelihood is there that my 100-line piece of code has an exploit in it versus how likely is it that Windows has an exploit in it somewhere, given that it's a gigantic program? Again, so the likelihood of my small piece of code might be 2 or 3%, but Windows is so large, it might give me a number like 64 or 70%, something like that. But once again, that's a regression problem because it's trying to map the input, which is the number of lines of code, and it's trying to give me a percentage likelihood as an output. So that's a continuous real valued output. And we're going to talk more about this and see an example of it in the upcoming slides. To add on to the previous slide a little bit, for each of the 2 types of machine learning problems, the 2 categories that exist, remember we said there's classification problems and there are regression problems. Okay, within each of those 2, there are 2 types of learning that can take place. So these can both take place for classification, these can both take place for regression problems. The first one is called supervised learning. And in supervised learning, we take the model, which is the machine learning algorithm, and we train it by giving it a bunch of data inputs that we already know the answers to. So we give it, let's say we're going to train the model to detect whether or not a particular mail message is spam. We're going to take samples that we know are spam and we're going to feed those into the model. And we're going to take samples that we know are not spam and we're going to feed those into the model. So the important thing when we say supervised learning, the data that we train the model on, we already know the answers to. Okay, so they're existing data samples that we already have labeled training samples for. So again, if I'm sending an email in, I label it as spam. If I have a legitimate email that I want to send in, I tell the model, hey, this is not spam. And that's how it knows how to learn. Okay, so the key here is that the data is labeled in a supervised algorithm, and then based on what the model learns, as we feed in email in the future, it will make predictions as to whether those messages are or are not likely to be spam based on the labeled training samples that we gave to the algorithm. Unsupervised learning works a little bit differently. In fact, it's just the opposite. So we still present a large set of data to the algorithm. So we may present it with, let's say, 5 million emails, but we're not going to actually tell it which emails are and are not spam. So although the input is the same, the input is nearly the same, the major difference is that we don't give the model or the algorithm labeled training data. We give it completely unlabeled training samples, and then we expect the unsupervised learning algorithm to come up with some intuition or find patterns in the data on its own. Okay, so like I said, the supervised learning and unsupervised learning can be used for both classification and regression problems. Okay, but in order to refine these models, no matter which method we're using, okay, the model is going to be iteratively revised by what we call a cost function. And we're going to talk a little bit more about a cost function in the context of linear regression in these next couple slides here. The first model we're going to discuss is something called linear regression. And if you think back to the last slide we just saw, we talked about a regression problem takes a value as an input, and then the output is a single value that comes from a continuous range of real valued numbers. Okay, so in this case, and bear with me, I'm going to try to actually draw on the screen here a little bit to make some things more clear. We'll see how this goes. And to help this idea stick a little bit better, I'm going to try to draw on the screen. So we'll see how this goes. Please just bear with me. Okay, so here we go. If you see the equation underneath the graph on the left, this might actually look familiar to you. It's actually just the equation of a line. If we rearrange these terms and we replace h theta of x with a y, and then we swap the two terms on the right-hand side, so theta 1 becomes an m, x1 remains an x, theta 0 becomes a b. So even though it looks a little bit fancier, it literally is just a line. Okay, so what you see here, you see the scatter plot, and we've generated a best fit line to the data. That's that red line there. So we may want to begin to make a prediction. I don't know what this data is. It's just a random example that I can try for you for demo purposes. But you can see right here that we want to make a hypothesis. That's what H means. We're going to come up with some hypothesis based on X. And the way we're going to calculate that is by doing theta 0 plus theta 1 times x1. And we'll talk about how to generate that in a little bit. But so basically in this example, you can see, let's say if you wanted to give me the number 30 as x. Okay, so 30 is an input. We come along the x-axis here, we see that here's 30, and we're basically just going to follow it up to our best fit line, which is our linear model. And then we're going to follow it over to the y-axis. Okay, so we see right here, this is our predicted answer. This is going to be our output. So it looks roughly like h theta of 30 is just about, say, 9. Okay, so again, h of theta, that's our hypothesis function, which is represented by the theta 0 plus theta 1 x1. So if you were to give me a value for x equal to 30, I'm going to drop it into my model, and I'm going to compute the y value for the corresponding x value that you gave me, and whatever that value comes out to be based on that best fit line through the data is going to be my hypothesis for what the answer I think will be. So that's my prediction. And so it's very easy. It's just a simple, like I said, it's just a simple line from algebra, and we don't have to worry about the details of fitting the best fit line to that data. We will talk about that in the office hour if you're interested, so I encourage you to stop by. But I did want to talk a little bit more about these numbers here, these thetas. So you see in this case, there's theta 0 and there's a theta 1 right here. Okay? So we actually call these parameters. And it turns out the way that we tweak these parameters is going to give us a better prediction based on some kind of cost function. Okay, so it's basically going to tell us how well does this line generally represent this data. And if we can make the cost function, or you could also kind of think of that as an error rate, if we can minimize that cost function or minimize that error rate by tweaking these parameters to give us better predictions, okay, the lower that cost function is, the better our prediction is going to be. So that might not make fully concrete sense yet, but like I said, stop by the office hour. We're going to do a fully worked example, and I'll be happy to show you more then. Okay, so again, this is just your simple linear regression. Again, we call it regression because we have a continuous range of real valued outputs and also a continuous range of real valued inputs. Okay, and based on this best fit line that we've drawn here, if you give me an x value of, say, 40, it's going to follow it up to that best fit line. I'm going to get the corresponding y value, and that's going to be my prediction. So that's a very simple first go at machine learning using linear regression. So here we are back at our linear regression. And remember what the point of that red line is. We believe that that red line is best fit to the data. So it sort of, in general, represents the average case given a bunch of points. And if we wanted to make a prediction, so if we wanted to drop x is equal to 60 into this model, okay, and get a hypothesis for it or make a prediction, okay, we're going to follow 60 up to the red line. So we're going to go through this point and we're going to hit right here. And if we follow that all the way over to the left, okay, so this model is going to predict that if the input, the x value is 60, it looks like the output value is roughly 14. Okay, that's the predicted value, or that's our hypothesis. But take a look here. Let's pretend that this dot right here is the only dot in the data set, which it looks like it might be, that's directly above 60. Okay, now remember, this is a training example. So this is a piece of data that we have that this has already happened. This has been measured and this was the exact outcome. So for an x equal to 60, we go up to the actual training example, and we're going to follow this all the way to the left. And it looks like we get a value of about 12. So we actually, in real life, we observed an example where x was 60 and y was 12. But look what the red line, look what our linear regression told us we would get. Right? If we follow 60 up to the regression line, remember we got a value of 14. So our prediction here using this line was a 14, but the real life example was a 12. Okay, so if we go back to the cost function slide, right here, h of theta of x, so our hypothesis when x was equal to 60, this was 14. But the y, which is the actual observed value, that was a 12. So you can see there's a little bit of a difference there. Our hypothesis was not 100% correct for x equals 60. Okay, so if you you subtract 14 minus 12, we get 2, and then we square that. Okay, so that was for the one data point, and then we're going to replicate that process for each and every one of these data points across the whole entire graph. We're basically going to say, how well does the red line actually approximate the value? So you can see right here, directly above 30, right here, 30 is a perfect prediction, which looks like a value of about 9 for this one data point. The prediction's spot on, so the cost function has no error. But if you look at this guy, right, the red line's a little bit too low, so the hypothesis is going to be a little bit low. And if you figure that this guy is also another observed training sample where x was equal to 30, right, the red line's going to overestimate it and think it's going to be too high. So it's a little bit low for this point, it's perfect here, and it's a little high for this one. And we're going to calculate those differences between each blue point and the red line, and we're going to add those all up, and that's what's going to give us our cost function. Okay, so that's all it is. All we're asking literally is, how do we choose our thetas so that the average error across all of those training samples minimizes that cost function? Okay? So if you have any questions, please feel free to email me about this. I know it might not be 100% abundantly clear, but as I said about the linear regression, we are going to do a deep dive into the linear regression and the cost function in this week's office hours. So please feel free to join us if you're free. In order to minimize the cost function that we saw on the previous slide, which again is just the least mean squared, remember that that just means the difference between our hypothesis and between the actual observed value. And then we take that across all sample points in our data set. Okay, we're going to use a method called, a method called gradient descent. And if you look at the math on the left, I think they put this in terms of vectors and functions and matrix transpositions, and I think it makes it look a little bit intimidating because the examples that I gave you in the previous slide were not vectors, were not matrices, right? We just did it in one single dimension with one feature, and that was that feature x1. But don't be disheartened because I think the next slide will make this all abundantly clear to you. But I did want to share some mathematical details for the folks who might be interested. And the first thing I'll say is that the hypothesis function that we use has to be convex. So if you remember back to your calculus days, you might remember concave and convex functions. A convex function is just a function that looks like your regular parabola, y equals x squared. In other words, it must go down for a period of time and it must come back up at some point. So it must have a minimum, basically. If it doesn't have a minimum, then our gradient descent is not going to take us down to a place where we can minimize our cost function. It may just, if it were a concave function, it would just take us down infinitely and we would never arrive there. Okay, so the function must be convex. And you also notice the term gradient. If you also think back to calculus, a gradient is very similar to a derivative. And if you think back to what a derivative is, a derivative of a line really just implies, a derivative of a function can imply the slope at that point. And indeed, that's exactly what gradient descent means. It means we're going to take the convex function that we have, and essentially we're going to follow the slope such that the function is decreasing. And we're going to follow it for as long as it decreases until it starts to go up again. As that cost function starts to increase, well, if the step before us we got a smaller cost function, or a smaller value for our cost function, and then the step after it, we got a larger value, and we know that our function is convex, that means we just went right past the minimum of the function. right? We can't go any lower. Now we're starting to go up the hill again, so we must be at the bottom of the hill, so we're going to stop. So I've included in parentheses here. Now this function can be nonlinear, that's fine, but there might be potentially many minimums, some of which are local, one might be maximal, but it is okay to arrive at a local minimum. It's just the thought that it's better to be at a minimum than it is to have a larger cost function that's affecting your hypothesis and making it worse. Okay? And then the only one other thing I wanted to point out here is if you look in front of the summation in the first line, you see the fraction 1 over n, and there's a little funny looking term right in front of it, n sub t. Okay, usually we'll represent this with the alpha symbol, and this is an important thing. It's called the tuning parameter, and it's going to control how fast we actually do the gradient descent. And we'll talk in the next slide, we'll see why that's important. But from a mathematical perspective, I know this is kind of a layman's introduction. I didn't want to hit you too hard with the mathy stuff, but these are the things to know. That the function must be convex. When we talk about derivative, we are talking about slope. We are hoping to converge to some minimum, be it local or maximal. And this alpha parameter is going to control the rate at which we actually perform the gradient descent. Now that we've gotten the math of gradient descent out of the way, this is kind of how I like to think of it. I think it's a pretty funny, but a very clear picture there on the right. As I said before, the general idea is this. We're going to start at some initial position, so we can select an initial value for our thetas. And then based on where you are, you're going to look to your left, and you're going to look to your right. And since the function is convex, like we mentioned in the previous section, either the left is going to lead you down, or the right, in theory, should lead you down. So if you're in position 1, if you try to go right, you're going up a hill. If you try to go left, you're going down a hill. So you're obviously going to follow the hill in the downward direction to try to hope to arrive at a minimum. Okay, the same thing for position 2. You can see if he looks right, he goes uphill. If he looks left, he goes a little bit downhill. So he's going to pursue the left direction until he starts to creep up that hill again, and then he'll know his previous location was a minimum. And same thing for C, but it's going to take C probably a little bit longer, or position 3 a little bit longer than position 1 or 2 to reach the minimum of C there. But there's no reason for him to go to the right. That cost function is growing very, very quickly, as you can see. So he's going to continue going to the left, creeping down that hill, as long as that slope is decreasing, that's the whole point of gradient descent, is following the slope as it leads you to a smaller and smaller value for your cost function. Eventually he's going to wind up down there at the bottom at C, and we'll have the smallest possible cost function, which will yield a value of theta for us to use as our parameter in our model. Okay, and as I said before, it's better to have, so you see that A is not as small as B and is not as small as C, but A is still a much better estimate for your hypothesis than being at position 1. Okay, obviously B is much better than A, and C is a little bit better than B. But again, this is an iterative method, so we're not necessarily expecting to get this right. You know, it has time to evolve, and based on new training data, it's possible that those parameters can change over time. Okay, so it's perfectly acceptable to arrive at a local minimum and then use that to generate your parameter value thetas for your linear regression model. The second machine learning model that we're going to look at is something called a neural network, and we hear about these a lot, and our discussions about them are centered around, or our discussions are centered around neural networks this week in the Google AI kits using a framework called TensorFlow. But I did want to tell you at a basic level a little bit about how these neural networks work. If you looked on the left-hand side here, you see 3 input nodes, and the neural network is basically just designed to simulate neurons in your brain. Okay, they don't act exactly the same, but roughly speaking, that's the idea. So these graphs can usually become very, very big. Instead of just the 3 inputs that we have here, it's not uncommon to have millions of inputs. So these networks can get very convoluted. But as you see, as you saw in linear regression, we had just one x input. We could have had multiple. We could have also had 3 inputs for linear regression too. There's nothing stopping that. Okay, but here we see that x1, x2, and x3 are the inputs, or also what we call features in machine learning. You also see that each edge has a weight associated with it. So for now, we'll just be very nondescript and we'll call those weights W1, W2, W3. So the weights just tell you how important each feature of the input is. So I'll bring some clarity to that in just a second. And then you see that they lead to this big node in the middle. The center node is something that we call a perceptron. So in neural networks, we're modeling neurons, okay, but they behave a little bit differently, and so we're going to call those perceptrons. And what the perceptron does, as you can see, it takes each weight, so W1, and multiplies it by x1, takes W2 times x2, W3 times x3, and then it sums those 3 weights together. So if you think of this in terms of vectors and matrices, this is just your typical dot product. Okay, so it's x1 w1 plus x2 w2 plus x3 w3. Okay, and then it's saying put that into some function. So this function is usually actually something pretty simple. It's usually something just like a threshold. So for example, and once again, I'm going to try to draw on the screen, so I hope you'll please forgive any mistakes. Okay, I think that still looks good. So let's say this neural network is trying to decide whether or not I'm going to go to work. Okay, I think that's something we probably face all day, or each day when we wake up, right? Okay, so let's say that our first input feature, x1, is, are we feeling well today? So the first thing we wake up and we think is, are we feeling well? And let's say that that carries a weight of 0.4, so about 40%. Okay, the next one is, let's say, do I need money? Okay, and let's say that has a weight of 0.3. And then let's say my third input or feature is going to say, do I have gas in my car? And that guy also carries a weight of, let's say, 0.3, so that our weights sum to 1. Okay, so it's, are we feeling well? Do we need money? And do we have gas? So, excuse me, let's say that our threshold function, let's say we have a threshold of about 0.6. In other words, y is going to equal 1 if it's greater than 0.6, and the output is going to be a 0 or a no, don't go to work, if the threshold is not met and the function evaluates as something less than 0.6. So you can see in this case, let's say that I am feeling well. So we have a 1 for x1. So 1 times the weight, which is 0.4. Okay. Let's say that I do need money, so that's also an input of a 1 times 0.3. And let's say I do have gas. So 1 times 0.3. Okay, and as you can see, 1 times 0.4 plus 1 times 0.3 times 1 times 0.3 That's going to result in a 1.0. Okay, and that's greater than 0.6. Therefore, we're going to output a 1, and we are going to go to work. Okay, so it's that simple. We just calculate the dot product of the inputs or the features times their individual weights. We add them up, and then our function distinguishes whether or not that summation or that dot product is greater than some threshold. If it is, it outputs 1. If it doesn't, it outputs a 0. So let's work one more example here. I'm obviously getting a little bit better with my sketching pen, sort of. Okay, get rid of that. All right. Okay, now in this example, let's say, am I feeling well today? The answer is no. That's a 0 times the weight, which was 0.4. Okay, plus, do I need money? Say no, I'm doing okay on money this month. It's a 0 times a 0.3. And do I have gas? Let's say the answer to that is yes. So the input is a 1, also times 0.3. Okay, if I do the multiplication here and sum them up, I get 0 plus 0 plus 0.3, which is obviously less than my threshold, which is 0.6. Therefore, I output is 0. So since I'm not feeling well and I don't need money, that means that this neural network has decided that I don't need to go to work today. Okay, whereas you saw before, if I did feel well and I needed money and I had gas, then I would have gone to work. But in this the second example here, you can see the neural network decided to output a 0. Okay, and similarly though, if I wasn't feeling well, that contributes a 0 times 0.4, so 0. I did need money, so 1 times 0.3, and I did have gas, another 1 times 0.3. That would sum to 0.6. So even though I wasn't feeling well, if I had a tank full of gas so I didn't have to stop on my way to work, and I was desperately in need of the money, then this neural network would send me to work, despite the fact that I may have been feeling a little bit ill. Okay, so I hope you enjoyed the demonstration on a neural network. We're going to look some more at this also during our office hour. So once again, this is probably the third pitch I made, but I hope you guys can make it because I do think it's pretty neat stuff. But if you have any questions, please feel free to let me know.